My name is Chris Landers. I'm from the Department of Energy, National Nuclear Security Center Administration. Great. I'm off to a good start, everyone. Well, these are unique times. So I'd like to just open up first saying thank you to the RRFM for continuing to host this conference. I think that this is a great opportunity for us to continue to be able to have these discussions and create these environments where we can continue to push our efforts forward in the nuclear community, in particular for our interest, the non-proliferation section. I'm really excited today to be with all the experts that hopefully you're seeing here on the panel with me. I'm excited to initiate a discussion on proliferation resistance. Recently, there's been a lot of talk about this, but we haven't had a lot of definition on it. But there's been a lot of increased discussion. There's recently been a CR at the IAEA. There's also been some language in the General Conference that just came out, as well as from the year before. So it's exciting to see the attention that's coming, and I'm excited to hear what the experts have to say here and how we can further define and begin to push these efforts forward. As I mentioned, I have a great group of experts here. We have Daniel Hergenretter from INVAP in Argentina. We have Lee Byung-chol from CARI in South Korea. We have Vladimir Kruchenkov from Rosatom in Russia. We have Miles Pomper from the Monterey Institute and the James Martin Center for Nonproliferation. We also have J.C. Dickerson from the National Nuclear Security Administration. Got it right that time. And we also have with us Dennis Vinson from Savannah River National Laboratory. The way that this will go is we have 45 minutes. I will ask a series of questions to the panel, and we will walk through that. Each question will be roughly 5 minutes, so we don't have a whole lot of time. We will save 10 to 15 minutes at the end for questions. And so as we are going through this, for those of you who are viewing, if you have any questions, please submit them via the chat function. Dennis will be gathering all of those questions, and will then send them to consolidate them and send them to me so that we can cover those in those last few minutes. So with that, we can begin, and I will start with my first question. And to start this off, Miles, maybe we can turn to you to respond. The first question, as we've heard from the IAEA, in particular Brian Boyer from INPRO, the definition of proliferation resistance is a combination of intrinsic features and extrinsic features to ensure that nuclear energy systems will continue to be unattractive means to acquire material for nuclear weapons programs. How can this vision of proliferation resistance be applied to research reactors, and does it need to be modified to do so? Kristen, I believe Miles is muted and I do not have the ability to unmute that. Could you help, please?
Sorry, sorry everyone, I forgot to unmute myself. Typical Zoom error. Good morning everyone from Washington. Chris, thanks for the question. So I think the idea of proliferation resistance can certainly be applied to research reactors. It's tended to be in the past, as you know, tended to be applied more to whole fuel systems and particularly fuel cycle elements, the back and front ends of the fuel cycle. But I think what we really need to, the modification really needs to be in terms of looking at some kind of graded approach. Nothing is perfectly proliferation resistant, and we need to have some kind of gradations in between of what is more or less proliferation resistant, and to determine and define our terms more narrowly. It's important since research reactors, as you know, have been used actually much more than power reactors for many of the nuclear weapons programs we have, unfortunately.
Okay, thank you. JC, could you also respond on that, please?
Sure. And I'm responding on behalf of our new proliferation resistance optimization program that we're standing up at the U.S. Department of Energy. And I think a key part of this definition is that there's no one-size-fits-all solution to increasing proliferation resistance. So what we're trying to do with ProX is gather all of the great ideas out there and really detail the lists of intrinsic and extrinsic measures, and then to develop a framework for finding the right combination of those measures in individual applications. And I think this will be even more useful as we look towards the future, and the new facilities that are being designed now are more innovative, and they're being used for specific purposes. They're using new fuels, new missions. So it'll be interesting. It'll be very important, but also very great use of our multivariate analysis and experience in dealing with challenging situations to try and look towards the future. Thanks.
Thank you. And let's take one more for this question. Vladimir, would you like to respond?
Thank you, Chris. I would add to that in principle, I'm satisfied in this definition. Important is to explain it in particular from our experience, as Rosatom is working in as a customer or potential customer of some nuclear facilities, including 7 countries. We carefully explain our potential buyers or potential customers what is the sense of proliferation resistance in the non-proliferation, and that's close to the subject of EIS safeguards. The materials should be safeguarded, and it then we connect to the nuclear material accounting and control. And many national authorities and operators or potential operators not necessarily familiar with the state system of nuclear material accounting control and facility system, and we share this to a certain extent. And of course important if we want to provide a research reactor into the centers nuclear science and technology, we try to make the reactor resistant from, it means that fuel it with low enriched uranium, and also to be sure that the production of plutonium would be small, for example, less than EIS threshold of plutonium 2 kilogram category 1 plutonium by that's physical protection category. And only after that we start terms of reference construction in the frame of this EPC project as usual.
Okay, thank you everyone. Moving on to question number 2. I'm sorry, did you?
So that's finally I can say on this subject that into action and accounting. Important to have such a reactors for developing that.
Okay, thank you, Vladimir. Vladimir, also we are getting a little bit of interruption on your speaking, so I don't know, maybe if the tech folks can get that worked out. But in the meantime, let's move to question number 2. And Daniel, why don't you start question number 2 for us? And so the question is, how are vendors and operators already designing proliferation resistance into the systems they are building or wish to build?
Okay, thank you. I think it is very important to supply to the customer a fit-for-purpose facility. So the scope of the nuclear facility shall be consistent with the stakeholder requirement, consistent with the availability of resources to operate and maintain the facility. I mean human resources, technical resources, and also economical resources. So from the technical point of view, according to the intended use of the reactor, different approach can be applied. to improve the proliferation resistance. For example, for high power research reactor or production reactor, okay, we used to have high discharge burn-up in order to maximize the fuel utilization and creating some isotope barrier to making the material less attractive. On the other hand, we can optimize the reactor power in order to minimize the fuel consumptions. Or in case of reactors that produce molybdenum-99, we prefer to use low enrichment target. On the other hand, in the small flexible research reactor for university or for training or for human resources development, the enrichment is used to be the lowest as possible, in sometimes lower than in nuclear power plant. In that kind of reactor, for example, we don't have a discharge burn-up, so the loss of reactivity used to be compensated by adding fuel or adding reflector. And these are the main technical aspects.
Okay, thank you, Daniel. Lee Byung-chol, would you also like to speak to that?
Yes, Korea, we are now constructing the Gijang Research Reactor. Its purpose is to produce medical isotope and neutron transmutation doping. When we start to design our KJRR, we selected low-enriched uranium and the high-density uranium molybdenum fuel. Its density is 8 gram U per cubic centimeter. It's about 70% higher than the uranium silicide fuel. So we get the longer cycle length, and then we can minimize the number of spent fuels. Also, we Korea have an Institute for Nuclear Non-Proliferation and Control, and we cooperate for the non-proliferation with the KINEC from the beginning of the KJR design. So with the KINEC cooperation with KINEC, and we have lots of experience from the Hanaro operation, and we have a physical protection system, and cyber security also was launched in the beginning of the project. So during the as the project goes on, those kind of physical protection system and cyber security is continuously should be modified and updated according to the situation changes. So that's our proliferation resistance approach when we are designing and constructing our KJR reactor. Thank you.
Wonderful. Thank you very much. I think actually, you know, some of the discussion we've had already leads very well into this third question. JC, maybe we could have you lead off with this one, but we've already heard from Vladimir about the linkage to safeguards and material control and accountability, and just now from Lee Byung-chol again about the linkage to the security and the safeguards and all of that. So for question 3, in your opinion, how is proliferation resistance different from safeguards and security?
Thank you. And I think we heard a little bit of it from Vladimir earlier, although I didn't hear all of his answer, but I think we're headed in the same direction. You know, I think there's a lot of overlap between the three, and often I think they're using sometimes the same tools, but for different purposes. So regarding proliferation resistance and safeguards. I think they share a focus on transparency of operation and accountability of materials, but specifically proliferation resistance measures should focus on making nuclear material production and diversion more difficult, time-consuming, and transparent. If well designed, though, proliferation resistance measures should also improve safeguards verification and inspection effectiveness by simplifying the verification process and reducing operator burden. And similarly, I think proliferation resistance and security share an interest in preventing proliferation by minimizing material attractiveness and control. But a key focus for proliferation resistance measures is to reduce the attractiveness of material throughout the fuel cycle. And again, if successful, because they're so well linked, effective proliferation resistance should also make security more effective. So it's we are talking about the same things, but from different perspectives, different places in the circle, I think.
Wonderful. Thank you, JC. Miles, would you also like to respond to that?
Sure. I mean, I was trying to think about this earlier, and I was thinking about sort of a metaphor for it. Is imagine sort of what we're worried about is sort of a gold vault, and you know, proliferation resistance in a sense is shrinking the amount of gold in the vault, rather than worrying about who's inspecting that, who's auditing it, and who's guarding that vault. I guess that's the way I differentiate it from the other two.
Okay, thank you, Miles. Let's move on to the fourth question, just to make sure that we're tracking time appropriately here. Lee Byung-chul, maybe I'll ask you to respond first to this one. The question is, how is proliferation resistance currently being communicated to the regulators, stakeholders, and the international community? And how can we improve the communication of proliferation resistance?
Korea has an act on the physical protection and the radiological emergency. That's a regulation applied to the physical protection about for the nuclear facilities, including research reactor in Korea. And then as I said before, we have a regulatory body for the nuclear non-proliferation and control, and the regulatory guides of the KINAC, K-I-N-A-C, are the basis for the proliferation resistance of research reactor. KINAC has regularly exchange of information on the stakeholders, or when some issues occurred, and what the to prepare some exchange of information in preparing the regular IAEA meeting, all the stakeholders gathered and then discuss about the exchange of the information on the non-proliferation and we have a regular online learning for physical protection, which is provided by KINAC, and we have also offline learning for the persons at the management level. That's written by the law. So that's a legal arrangement, and I think we can improve the exchange, discussion of the on the example or the sharing of the experience or knowledge, then that kind of activities on sharing of knowledge or lessons could improve the proliferation resistance. Okay, thank you. That's my opinion.
Okay, thank you very much. Daniel, could we also ask maybe you to respond to this as well?
And speak.
Okay, thank you. I think there is an experience in the agency related to the effort in the proliferation resistance, particularly through the IMPRO program that has focus in the front-end fuel cycle facilities and nuclear power plant. So I think a similar approach can be followed for research reactor to improve the communication with the regulators and stakeholders. For example, throughout the publication of a technical document with the guidelines to enhance the proliferation resistance in research reactors. So in that case, the proliferation resistance shall cover all the stages of the research reactor, from the design, construction, and of course, utilization. I think, as in many activities, the good communication is always important. In particular, in nuclear project, there is a need to communicate the importance of proliferation resistance from the beginning of the stage of a new project. And I think a good communication will be possible to obtain the support of the community and the support of the government to the nuclear project. Thank you.
Okay, thank you, Daniel. I will now move into the last question that is scheduled. So I'd like to just remind everyone watching that if you do have any questions on what we are discussing with the panel and the various experts, please submit your questions, and those will be consolidated and provided to me, and then we can raise those at the end of the panel. If we don't have those questions, there's a few follow-up. If we don't have any questions from the audience, there's a few follow-up questions that I can provide to continue the discussion. So for the last question, Vladimir, it's good to have you back. I apologize for the technical difficulties, but I will ask you to respond to the last question. How can focusing on proliferation resistance improve nuclear security and increase scientific and industrial benefits to the facilities and their countries?
So I hope you hear me. Thank you. First of all, these improvements, keep in mind that the facility, the research reactor, is resistant. In that sense, it's easy for operators to arrange interesting industrial or medical application. I think now more and more the interest to radioisotopes for medicine. I can give an example of production of molybdenum-99, but still there are by use of research reactors. And if the reactor is fueled with LEU, still there were technologies in old times when the neutrons radiated highly enriched uranium target to produce fission products, including molybdenum-99, then transforming to technetium. But a recent program of EIA, supported by member states, provided the opportunity to replace the highly enriched targets to low enriched targets. And that actually also the contribution to proliferation resistance, because then much less concern and much less attractiveness to both to the fuel and to the targets irradiated for production of this isotope. And there is a competition between reactor production and accelerator production. Accelerator production does not contain any proliferation resistant concerns, but the productivity is small, photonuclear reaction, for example. So that means a good proliferation resistant research reactor contributes a lot to stable and useful production of radioisotopes. And as I was missed a little bit, allow me to say something about distinction between nuclear security and safeguards and proliferation resistance. Do you allow me?
Yes,
So,
please.
again, nuclear security has a broad scope, including not only prevention of unauthorized removal of materials, but also protection from radiological sabotage of nuclear facilities and materials. But the physical protection elements against sabotage also contribute, for example, strong containment against air attack. They also contribute into the prevention of unauthorized removal of materials. And also another example, again, relates to my IAEA experience. IAEA initiated more than 20 years ago a program of incidental trafficking database available to many member states. And there were cases, most of the cases incidental, but not intentional. It's orphaned radioactive, more radioactive, but also were cases nuclear materials were detected, including the cross-border radiation monitors. And there were some cases of fuel, small quantities of fuel of research reactors. And if member states communicated about that and on the special communication channels, they better understand that the non-proliferation is under control and it provides good contribution for future assurance about non-availability of fissile material for the non-civilian purposes. So this, I think, also important role of nuclear security.
Wonderful. Thank you very much, Vladimir. And it's good to have you back. You're very clear and we can see you and we can hear you. So good to have you back. Thank you for that. At this time, I will move into the questions that we're receiving from the audience. The first question is an open question. So to the panelists, if you would like to respond, please just raise your hand and then I can call on you. The first question is, what new fuel design and development activities are focused on proliferation resistance? Would any of the panelists like to address that? Well, let's just go ahead and I'll go ahead and pick someone. JC, you had mentioned that you are now leading up a new proliferation resistance program. Would you like to respond to that question?
Can you, I was just about to ask, could you read the question one more time?
Sure. The question is, what new fuel design and development activities are focused on proliferation resistance? So my take on that is, are there activities out there right now that are looking at designing or developing new fuels that will help with proliferation resistance? So maybe JC, and then we'll go to Vladimir after JC.
Great. I don't, I'm still new to the world, to this world. I can't get into many of the specifics, but I think it's important to include fuel characteristics and discussion of fuels, vital to include fuels in, talk about proliferation resistance, because it's, one of the keys to making sure that our proliferation resistance is strong. I think there are many ways that we have improved proliferation resistance by reducing enrichment levels. But as we've seen, from the innovative capabilities of this community, that we have a new generation of challenges ahead of us. So there are lots of new fuels being developed, and I know we're eager to take a look at those, even at lower enrichment levels from a proliferation resistance standpoint, and make sure that they're both effective and secure.
Wonderful. Thank you, JC. Vladimir, you'd raise your hand?
There is one old example which already implemented. There were several research reactors in the world of US origin, of Soviet origin, operating highly enriched uranium. And there was a program of conversion of these reactors from HEU to LEU, but to stay within same the core of the reactor, and then that it was a need to increase the concentration of the density of uranium, and the uranium oxide fuel was replaced in the US, I remember, in other countries by uranium silicate containing more uranium in the cubic centimeter of the fuel. And it allowed to convert HEU to LEU reactors. So also there is are prospects for molybdenum uranium fuel also for existing reactors. That's example, and molybdenum uranium with higher density of uranium could be used to convert, to modernize existing reactors to LEU. And other more related to new reactors, if you increase the burn-up of fuel and increase intervals between refueling of reactor from several months, for example, to several years. I know it's going on now for power reactors, but also then it means that's the time when the fuel is removed from the core of reactor is an attractive time to get unauthorized access to this fuel. And now the long-term burn-up fuels, first of all, they provide plutonium of a lower quality for proliferation. That the concentration of plutonium-239 is lowering and lowering. It means that this becomes, the fuel becomes less attractive for proliferators. And also, of course, that's refueling periods. Periods between refueling are very important from that sense.
Thank you, Vladimir. Daniel, I saw you also raised your hand.
Yes.
Before you respond to that, feel free to respond to that, but I also have another question that maybe you could respond together. The second question is, larger systems are clearly a higher level of concern due to fuel inventory. Fortunately, the benefits of compact cores has evolved in the community. How do vendors consider compact cores and reduction of unnecessary complexity in the design?
Okay. Yes, I think if in order to enhance the proliferation resistance, I think new fuels should increase the burn-up in order to create some isotope barriers to make more to make less attractive the material for other uses, and also maybe adding some components in the pellet. We can create some chemical barriers in order to make more difficult the separation. Related to the high performance research reactor with very compact core, okay, it's difficult to increase the burn-up because the small size of the core, but the effort can be focused in order to optimize the reactor power in order to obtain a balance between burn-up and fuel consumption that could make appropriate to enhance proliferant resistance. This is.
Okay, thank you. Yeah, Lee-Byung Choi, would you also like to respond to that? It was the question about the sizing. So larger systems are clearly a higher level of concern due to fuel inventory. Fortunately, the benefits of compact cores have evolved. And how do vendors consider compact cores and reduction of unnecessary complexities in their designs?
When we designed the compact core, we have some limitation on the system, the operating environment, such as coolant velocity, heat flux, all those kinds of parameters related with the neutronic performance, and the thermohydraulic parameters are related in designing the compact core. I think when we design, generally we analyze in the neutronics characteristics, some hydraulics behavior and safety analysis. We should include some uncertainty, but when we optimize, when we design the core, each discipline area have some margin. So those kind of uncertainty are added altogether in the system design. The actual the margin from the design is a little bit higher than the actual. So I think if we can be able to decrease those kind of uncertainty in designing, in the nuclear design or some hydraulic design and the safety analysis, then we can make the core a little bit more compact.
Okay, thank you. A follow-up to that, and I guess this will be the last question that we have from the audience, and then I'll have one closing question. The next question would be is, how can advances in instrumentation and control help with proliferation resistance? Vladimir, do you want to maybe respond to that one?
Thank you. I think that intermittent control systems now operated by digital systems, and of course, the cybersecurity or computer security, as we call it, plays an extremely important role on the protection and indirectly to the proliferation resistance. So, and also these automatic systems allow to reduce the personnel operating with the reactor, including maybe research reactor, and means that's the less personnel, the less opportunity for insiders to be introduced into the operating team. Of course, it's not necessary on size of personnel. It's much more complicated. Nevertheless, it contributes to security and then to the proliferation resistance. And I personally support this trend for automatization and digital systems for the reactor operation. Of course, still these systems need a certain level of protection, not only from the computer point of view, but also some patrolling of them may be necessary to check for tampering of the system.
Okay, thank you very much. Well, I'll end with one more question here. There was a lot of discussion here about, a lot of good discussion here about the definition of proliferation resistance. Where does it cross lines? What are technologies that can improve proliferation resistance in terms of fuels, right sizing of facilities? Miles had mentioned earlier too about typically it goes from all the way from the beginning to the end, field fab to field disposition. So there's a large spectrum here about where it defines. And there was a lot of discussion too about communication. And so I guess one key thing here seems like is what are really some of the next steps that can be done by the international community to pull us all together, and so that we are all focused on the same point and moving in the same direction. There's a lot of broad discussion so far, but it seems like everyone is generally thinking the same thing and moving in the same direction. But what are some of the key next steps that need to be done? And maybe Miles, would you like to respond on that one?
Well, I think the crucial next step is to really agree on terminology, because I remember a few years ago when we had the US and Japan and South Korea had the deal to supply nuclear reactors to North Korea as part of the framework agreement, and people were calling the light water reactors supplied to North Korea proliferation resistant, which really not that, they're more so than a heavy water reactor. But what do we mean by these terms? We need to say, this might be 20% proliferation resistant, this might be 50%, and in different directions and different, the different characteristics that apply to that. But I think we need to have a universal agreement on what those terms mean and and how they can be applied.
Okay, Thank you. Daniel, would you also like to respond to that?
Yes, thank you. Yes, I think maybe the next step could be to analyze if it's possible to perform something similar to the already performed for nuclear power plants. That means maybe analyze to perform to make a publications or a technical document in the agency with guidelines to enhance proliferation resistance.
Okay, thank you. Well, with that, I will summarize what I kind of took away a little bit, and then we will close it out. I guess before I even do my summary, I would like to again thank RRFM for continuing these discussions so that we can get together like this and hear each other's views and point ourselves in a common direction. I'd like to thank each of our panelists. This was a very exciting discussion for me. And like I said, it's something that has been talked about for a long time, but really has been starting to get a lot of momentum lately. And to be able to pull us together and hear each of the different views and perspectives and see that we have a common vision, but yet we are talking slightly different, and getting us together it's an exciting time. I see there was definitely a lot of discussion about communicating so we get on the same page with definitions. I think that's critical, and I think, you know, as we saw there at the very end with Daniel saying maybe the IAEA and continued meetings there and tech documents to kind of formalize definitions and what our next steps sounds critical. It sounds like continued engagement at the technical level in terms of understanding instrumentation, understanding fuels, understanding once we have these kind of guidelines, what can we do together in the institutes? I know personally all the national laboratories that I work with are now excited because they're like, this means Chris is going to fund us more to go do more stuff. So, but I think that's I think a technical engagement is really needed. And I appreciate also the non-governmental organizations continuing to keep the focus where it needs to be in terms of what are we doing for the next steps, and not just staying where we're staying with what we are doing, but looking at that next evolution. So I think there's a lot of potential future with proliferation resistance optimization activities. And I'm grateful for everyone coming together and having this discussion. And with that, I believe, I don't know exactly how this will end. I think we just disappear. So thank you everyone for listening. And I hope that this was fruitful and everyone enjoyed it. Thank you to my panel, and thank you to RFM and Dennis for pulling all those questions together for me.
Thank you, Chris, as well.
Yes, yes, thank you.
Thank you.
Have a wonderful Tuesday or Wednesday or whatever day it is, wherever you are in the world. Thank you.
Okay, thank you.